Hi gemologists, welcome back to the third video here at Hunt Country Jewelers Kids Gemology Detective Videos, where we will be doing some further testing on our mystery gemstones, and we will at long last figure out what they are. First, we will be using magnification to see onto and into our gemstones. We'll use some gemological instruments called a Polariscope and a refractometer to bring us to a conclusion and identify our mystery gemstones. In order to do this, we'll need our loupes, reference cards, worksheets, pencils, and tweezers to record our data. We are going to look at the gemstones through magnification. Whether we do that with your loupe, which is a 10 times magnification, or with our microscope here, which ranges up to 40 times magnification, we do this to help us observe what the gemstone looks like on its surface and also inside the crystal. Your loupe is plenty strong to be used to see what we're looking for today in your gemstones. So feel free to practice with your loupe on the stones in your kit for today. Regardless of what instrument we are using to magnify our gemstones, the very first thing we need to do is to get past the glitz and the glamour that a faceted gemstone has, so that we can objectively quantify what we're looking at. Most commonly, when we say gemstones, we think of faceted gemstones, where each flat, called a facet, is ground into place on a wheel. We'll come back to this part. There are several ways a gemstone can be fashioned or cut, including cabochons, beads, carvings, among many others. But before a gemstone is cut at all, it is called rough. So this is a piece of sapphire rough, for instance. Our two mystery gemstones are both faceted, so that's where we'll keep our focus today. Before we begin, let's define the geography of a gemstone. Looking at a faceted gemstone, the perimeter defines the shape. The layout of the facets within that shape is called the pattern. There are many patterns of gemstones for any given shape. Some are more common than others, but regardless, they'll all have a few general terms in common. The top of a gemstone is called the crown. The bottom half is called the pavilion. Where the two meet is the girdle. The flats are called facets, and where the facets meet are called facet junctions. The big facet at the top is called the table, and the term cutting, it's rather confusing. Gems are actually fashioned by using various methods of grinding on the surface with different grits until a polish is achieved. Everybody still with me? Surface condition is important for many reasons. And remember, there are always exceptions to this, but often extra time is dedicated to the cutting and fashioning of a natural or more important gemstone. Glass, plastic, and other materials that are trying to look like gemstones don't typically warrant the extra time and attention in cutting. Very often, this difference in surface quality is quite visible. And as gemology detectives, these are surface quality observations we will want to note to help us figure out what our mystery stones are. So let's look at our first mystery stone and get right into our list of observations, and we'll include some references as we go. We have already recognized this stone to be transparent, a green color, light in tone, with high saturation. The list of initial observations on the surface would include the following. What is the shape of the stone? It's a cushion, like a pillow. What is the gemstone's pattern? This is a fancy pattern. It's complicated and very well done. How symmetrical is the stone? Symmetry, very good. Table is centered. There is a nice, clearly repeated pattern. It's not perfect, but it's very good. As a whole, the overall execution is very good. Now let's look at the surface quality of the gemstone. We have nice, flat facets and crisp facet junctions, as opposed to rounded corners. A softer corner could lend itself to being a softer mineral, like quartz, or non-gemstone materials, like glass or plastic. So what we just did there was a quick overview of the surface quality of the gemstone, including its shape, pattern, and execution. Why? These are the clues that help us to form the larger picture of what our mystery gemstone is. Our stone here is a fancy shape. It's symmetrical, well cut, with a clear idea behind the facet pattern chosen. This tells me that someone spent a great deal of time and effort on this stone, making it look as good as possible, which potentially increases the chance that it is a natural or valuable material. Now, we're going to get out your loupe and our microscope and take a look inside the gemstones. Clarity, in regards to gemstones, is defined by GIA as a gemstone's relative freedom from inclusions and blemishes. Inclusions are traits inside the crystal, and they can be solid, liquid, gas, or any combination of the three. Blemishes are traits on the surface of the crystal. Most natural gemstones have inclusions somewhere, and they are not necessarily a bad thing. Inclusions can even be viewed as beauty marks, and they're important to gemologists for multiple reasons. Let's discuss them as we're viewing our mystery gemstones. The first few things that I see here are crystals and groups of small crystals that we generically called fingerprints, because when you view them all together, well, they look like a fingerprint. These could have started as a feather and rehealed or reformed in a fingerprint-like fashion. A feather is a general name for a fracture somewhere within the stone, which we can clearly see visible here. But the important part is that we have well-defined, complete crystals inside the stone with flat crystal faces, and that is an excellent indication that this is a natural gemstone. Synthetic and man-made minerals do also have inclusions, but they look quite different from these. There are times when a gemstone can have a specific inclusion that conclusively identifies a specific mineral. For example, our peridot from video number 2 has a lovely lily pad inclusion, which practically guarantees you are looking at a peridot. Let's go ahead and fill in our observations under magnification for mystery gemstone number 1. The things that are noteworthy on the surface are the well-executed cushion pattern. For the interior, we have natural crystals and feathers. Let's take a look at mystery stone number 2. Again, we've already labeled this gemstone as greenish blue with a dark tone and intense saturation. Just on the surface, we see that it's a barrel shape, like the old wine casks. It's quite symmetrical, with nicely formed facet junctions, and the facets are flat. Someone again spent some time on this stone. Check this out though. We seem to have a flake missing. Sometimes cutters will leave the original skin of the piece of rough still on the stone. This is called a natural. And here's another on a different corner. Typically, this means that the material either isn't valuable enough to be worth the time to cut them out, or it is so valuable that it's not worth the weight loss to the stone to remove it. Now, irregularities just on the surfaces are called blemishes, as we mentioned previously. Looking into the stone, the middle looks very clean and lacking inclusions. But the cutter did leave some inclusions on the end of this gemstone. And considering the time and effort given to the rest of the fashioning, I am thinking that they wanted to save as much of the stone as possible, which agrees with our theory that the natural on the surface is an indication that the material is valuable. The inclusions themselves look to be more fluid inclusions and unhealed feathers. So this doesn't seem to be glass or a common synthetic material. So let's record this on our worksheets before we get into our last section, in which we'll discuss how light enters and travels through gemstones. Mystery stone number 2. On the surface of this gemstone, we have 2 naturals, otherwise also very well executed. And internally, we have fluid inclusions and unhealed feathers. The refractometer and polariscope. When light enters a new medium, it changes direction, or bends. This is called refraction. Refractometers are used to measure this change of direction. So essentially, we can use refractometers to measure how much a gemstone bends light. We will come back to this shortly. The second machine, called a polariscope, shows us if light is merely bent when it enters the gemstone, or if it bends and splits into 2 beams. And this splitting of light isn't because of the facet patterns or the inclusions, but because of the actual structure of the crystal. When light enters a transparent gemstone, it can either bend, continue through the stone and exit, which is called being singly refractive. Light enters the gemstone, changes direction, but stays as a single beam and then exits the stone. The other option is that when light enters the gemstone, it splits into 2 beams, which both continue through the stone and then exit. This is called being doubly refractive. Light enters your gemstone, changes direction, but also splits into 2 beams and then exits. With the exception of a few specialty cases, if the stone is transparent, it will either be one or the other, and we can test for this using an instrument called a polariscope. A polariscope is a very simple instrument. We have a light at the bottom, a lens, some space, and a second lens. These lenses are a little special. They are actually polarized filters, which means they have tiny lines all parallel to each other, all going one way. So when we line up the polarized lines between the 2 lenses, nothing happens. The light comes straight through. But when we move to cross the polars, putting the lines perpendicular to each other in both lenses, the light goes away. This is because the first filter stopped all of the light going in one direction, and the second filter stopped all the rest. So what happens when we put a gemstone in between our 2 polarized lenses and rotate it around a little bit? Do we see any light coming through the gemstone? Yes? How? Well, we just said Some gemstones can split light into two beams, and as it turns out, light comes through the first polarized filter and then into our gemstone, and it's only going one way. But once it enters the gemstone, it splits, and now it's going two ways. And the second filter can only stop that original beam. The new beam is what exits out the second lens and comes to your eye. So when we see a definitive light blinking on, off, we know this gemstone is doubly refractive. So what do you think will happen with a singly refractive gemstone in the Polariscope? It stays dark. Mostly dark, anyway. Even if there is an errant touch of light coming through that is inconsistent, we are looking for a clear pattern of light and dark blinking. If this is absent, it is because the light comes through the first filter and gets reduced to going only one direction. And when it goes into the stone, it bends a little, but continues out in that same direction. And the second filter stops all of the rest. So a singly refractive gemstone will stay dark, no matter how much you move it all around. So with one single test, we have eliminated half of the options of what a gemstone can be. Let's take a look at our actual mystery gemstones and see what they are. Mystery gemstone number 1. I see no clear pattern of light to dark blinking. So this stone appears to be singly refractive. Mystery stone number 2. There's a clear light to dark blinking as we move the stone around, so this stone is doubly refractive. Let's record these observations on our worksheets. Mystery stone number 1, singly refractive, and mystery stone number 2, doubly refractive. Just as a side note, we can see the doubling effect of a doubly refractive stone in mystery gemstone number 2. Compare the pavilion of mystery stone number 2 on the right and number 1 on the left. In stone number 2, the facet junctions have been doubled, as in it looks like there are two of them right next to each other, because there are. Whereas in mystery stone number 1, that phenomenon is not seen at all. So we keep saying light bends. What do we mean by that? Let's look at an example with a plain glass of water and a regular straw. We add the straw to the water. Notice how the straw doesn't appear to be in a straight line anymore. That's because as light travels through different mediums, its speed will change, causing the light to bend. This is known as refraction. So in this case, the light travels at one speed through the air and changes when it gets to the water, making the straw appear to be bent, even though we know the straw is straight. Gemstones also slow down light when it enters, causing the light to bend, and each mineral has its own unique amount that it slows down light, which is called its refractive index. We can measure this with an instrument called a refractometer. A refractometer is also fairly simple in that light enters through the back, gets reflected through a half hemisphere of a controlled substance into the gemstone, which then bends a little and gets bounced back down into the machine, off of a scale, and back up to where it is displayed on an indexed set of numbers for us to read. Simple. Now the one complication is that to get the light to travel between the machine and our gemstone, we need a contact liquid, or refractive index liquid. Our RI liquid can measure up to a certain number, which in this case is 1.81. Now, some gemstones do have a refractive index over 1.81, and we call those stones OTL, for over the limit. In those cases, we don't get an exact RI reading, but we can rule out all gemstones that are not OTL. For those who are interested, RI liquid is mostly methylene iodide with some tetraiodiethylene thrown in, and I highly recommend you don't drink it. Let's give it a try with our first mystery gemstone. We put a small amount of contact liquid between the stone and the refractometer, stone on, and I see a value of 1.74. Let's record this on our worksheets before continuing on to mystery gemstone number 2. Mystery stone number 1 has an RI value of 1.74. On mystery stone number 2, I get a value of 1.62. Again, let's record that on our worksheet. Mystery stone number 2 has an RI value of 1.62. This is a very convenient test for any stone that is loose or that we have easy access to the surface. However, many times gemstones are already mounted in jewelry, and it prevents us from being able to do this test at all, which means we rely even more on our other observations to come to our conclusions. Fortunately, with our 2 mystery stones, this isn't a problem, and we can go ahead and look at our recorded data and compare it against our reference materials. Again, gemology is a process of elimination, and we have already ruled out some options due to color, transparency, and fluorescence. For mystery stone number 1, we removed ruby as an option due to color. And glass is not an option because our gemstone fluoresces bright orange, and glass is inert. Looking at the options left, we know our gemstone is singly refractive, so emerald, peridot, and tourmaline are all now immediately removed as options, leaving diamond, CZ, and a green garnet called tsavorite. Now, if we look at RI values, we see that both diamond and CZ are much higher, both being OTL, and we had a clear reading at 1.74, which matches tsavorite garnet perfectly. So just to be sure, we can look at the inclusions of negative crystals with feathers, and once again, we have a match. Mystery gemstone number 1, it's a light green tsavorite garnet. For mystery stone number 2, we have already ruled out ruby and emerald due to color in our last video. So looking at our reading on the Polariscope, doubly refractive, we can now eliminate diamond, tsavorite garnet, CZ, and glass from our options, leaving peridot and tourmaline. Tourmaline's refractive index is listed as 1.616 to 1.65, and our reading of 1.62 definitely fits right in there. Plus, we have liquid-filled inclusions, which are noted below in the inclusion description for tourmaline as well. So for the final confirmation, even though peridot's RI is close, it only forms in green to yellowish green, and our stone's dominant color is blue. So peridot isn't really an option anyway. So mystery gemstone number 2 is a greenish blue tourmaline. Congratulations, gemologists! Not only have you identified what our mystery gemstones are, you have done so by learning how to objectively observe gemstones, to notice patterns in our data, and then to use these tools as a process of elimination to bring us to our conclusions. Both of these minerals are found found in nature and cut into the faceted gemstones that you see here. Both minerals are valuable and rare, lending to the extra time taken in the faceting process to preserve as much of the mineral as possible. And yet it's cut in a way to best display its color and the optical properties of the stone for us to enjoy. In the previous video, we mentioned that color and other physical properties affect value. Combining that with this video, we can comfortably say that in general, clean colors in high saturation medium tones, and the fewer the inclusions the better, the higher the potential value. Specifically valuing gemstones is complex and is a related but separate conversation from identification. On that note, in our final video, we'll take one more formal look at the stones in your kit and put this all together to identify exactly what they are. Beyond that, in future videos, we hope to explore in even more detail the world of gemstone identification, and we hope you'll join us for that as we continue on in the miniature but wonderful world of gemstones. Welcome back to Hunt Country Jewelers and surface conditions on the refractive index machine. Methylene iodine with some tetraiodine methylene, some tetraiodiditis, tetraethyliodiditis. I'm not going to be able to do this. Methylene iodide with some tetraiodiethylene mixed in, and it's delicious. Just kidding, don't drink it.